Hey, this is the example of what we just went over on the other one where we didn't have an equation. We just kind of went through what we did. So this INB, we're going to follow through a specific problem, and we're going to talk about it as we go. So we learned that symmetry with algebraic defense means I want to test this function for symmetry. Now, I should be able to look at this. If my symmetry is whether my function is even or odd, I can look at my powers right away. Right? And first of all, notice that I have a mixture of a odd power, cubic, even power, quadratic, and odd power, linear, and I have a constant term. Whenever I have a constant term, there is no way I can be an odd function because an odd function, all the signs have to change. And guess what? A constant never changes. So that positive 8 will always be there. So I know it's not going to be odd. I also know it's not going to be even because I have odd powers. I have a cubic term and I have a linear term. Those signs change when I plug in a negative x. And if it's going to be an even function, none of my signs can change. They all have to have even powers because that takes the negative 1 that I'm going to input when I plug in negative x, and it's going to change it back to a positive x, not impacting my term at all. Even though I might know that this is going to be a neither by looking at the polynomial, I still need to show that by my with algebraic defense. And that's what I'm going to do here. Plus, on our next step, we're going to need this function, so it's not going to be worthless. So I'm going to plug in a negative x everywhere I see an x, keeping everything the same, just changing my x to a negative x. Okay, and you might want to put a 1 or my power of 6x to the 1 power. And then I'm going to look. And it's all about, is my power odd or is it even? Okay. So my odd power, right, which is this cubic, if I raise -1 an odd amount of times, it's going to come back negative. So it changes the sign. It was positive, but the -1's going to stay. So it comes to a -1. Next is my even power. It's the quadratic right here. And if I take -1 and if I take negative x and go negative x times negative x, I get a positive x squared. That negative sign is going to go away when I raise it to an even power. So I just have this positive x squared times -3, which stays -3x squared. So the negative x does not impact my term at all when it's an even power. When it's an odd power, like the very first one, the negative stays, so it changes the sign. That was originally what it was in the polynomial was positive, so now it's negative. Again, do the same thing here. I have another odd power, so I know it's going to stay the negative sign, so it's going to change and say -1 times -6, which is a positive 6. And I know my constant never changes. Okay, so this result is, notice it's obviously not the exact same function that I started with, which was x cubed minus 3x plus, minus 6x plus 8. And it's not exactly the same equation because my cubic and my linear term changed signs. So this is what we call a neither. But more importantly, I'm asking for symmetry. So this thing is going to have no symmetry. Okay. And a lot of times they have no symmetry. That's a pretty common thing. I mean, the likelihood that you're going to run into a lot of polynomials that have all even powers or all odd powers is less likely versus having a mixture of odd and even powers. Okay. So Descartes' rule of sign says two things. It says I can talk about my functions x-intercepts or all their roots by looking at the original polynomial and the polynomial where I plug the negative x in, which I already have up here. Just that it's the same thing that I would do if I'm testing for symmetry. Okay, and what we're going to do is we're going to look at what are the sign changes between each term. Okay, so I'm going to start off at this original equation on the top, and I'm going to look at what are the sign changes starting with the x cubed. Well, it's a positive x cubed, and it moved to a negative 3. So from a positive 1 to a negative 3. So that changed signs. So that's one sign change. So I'm going to write 1. Then I went from a negative 3 to a negative 6. I did not change signs. So I do not have another sign change. Then I went from a negative 6 to a positive 8. So I had another sign change. So this one had 2 sign changes. Okay, that's all we need to know. It's a pretty easy test. We're going to do the same thing with the bottom polynomial when the negative x is plugged through. Obviously, if this was an even function, you'd have the exact same function again, but we didn't. We had an either. So I went from a negative 1 to a negative 3, no sign change. A negative 3 to a positive 6, one sign change. A positive 6 to a positive 8, no sign change. So I had one sign change. Okay. Now what I'm going to do is create a table. And then we'll talk about what this tells us. So I'm going to create this table. And I'm going to have some headings. So I'm going to say my positive x-intercepts or solutions, my negative x-intercepts or solutions, my possible number of complex or imaginary solutions, and then my total number. Okay. Well, the total number is your degree of your polynomial. So what is the degree of my polynomial? It's 3. So every time I'm going to come up with these combination of possible, positive, or negative, or imaginary, they have to total 3. Okay, so the first time that I go through these, it will usually, my sign changes will predict with no imaginary solutions. So I know that didn't make sense right away, but this is what happens. On this first one, where it was the original equation, however many sign changes is your possible amount of positive x-intercepts or solutions. So I'm going to write 2. On the one where we plug the negative x in, the number of sign changes is the number of possible negative x-intercepts. 1. Now notice 2 plus 1 is 3. I'm already at my total number of solutions that I'm allowed because this is a third degree. So I'm going to say, you know what? There are no complex or imaginary solutions in this first case. But yesterday, on Wednesday, we talked about, hey, a polynomial function can have complex roots, and they come in pairs. Okay? So what happens is this test only assumes rational, real solutions. It doesn't know about complex or imaginary solutions. So we have to come up with cases knowing that there's a possibility that this polynomial might have some complex solutions. So I'm going to create however many cases that I can with my complex ability. Now here's the one rule. Complex solutions come in conjugate pairs, so they happen in twos. Now notice I have 3 solutions all together with my first case. When I pull out the possibility that my polynomial has imaginary solutions, I can only pull them out of one category, meaning I can pull 2 out of the positive or 2 out of the negative. I can't say one of them out of the positive x-intercepts and one of them out of the negative. So the only category that has a possibility of giving up 2 solutions is my positive. Okay, so I'm going to say, well, maybe these positive these two positive x-intercepts, maybe they're not really there, and maybe they're really two complex conjugate solutions. So I'm going to transfer them over there. I still have my one negative, and I have a total of 3. Okay, now I would create a third scenario if I could do one thing. If I have the ability to pull 2 more out of one category, which is not possible because I have only one negative x-intercept possible. So I don't have 2 to pull out of that one. So these are my 2 cases what might happen. So case 1, I have 2 positive x-intercepts, 1 negative x-intercept, and no imaginary or complex. Case 2 that might happen is I might only have 1 negative x-intercept, and I might not have any other x-intercepts, and so I might break it down to a quadratic and use the quadratic formula and solve for my complex or imaginary solutions. Okay, so now what I want to do is do my rational root theorem, and that is my P over my Q, where P is my constant and my Q is my leading coefficient. This is a pretty easy test, okay? And so what you're going to do is you're going to first find what those two numbers are. Go all the way back up to the top, which is my constant was 8 and my leading coefficient was 1. Now what I want to do is list all the factors, both of those numbers in the numerator and denominator. So the factors of 8 are 1 plus or minus, 2 always plus or minus, 4, and 8. And my leading coefficient, well, the only factors of 1 are 1. Now what I want to do is write out my possible rational, which means integers, positive, negative accounting numbers, or anything that comes out of fractions. So it doesn't account for square roots or imaginary. So possible rational x-intercepts. What I want to do is create as many numbers as I can with all of these numerators. So I have a 1, a 2, a 4, and an 8, and they're all to be divisible by 1. So 1 divided by 1 is 1, 2 divided by 1 is 2. So it just happens to be all of these numerator numbers. Okay. If I had another, if my leading coefficient was like 2, then I would have like a plus or minus 2 here. So then I would have to divide all of these top numbers by 2 to create more. That would give me a larger pool of numbers. So right now I have 1, 2, 3, 4 numbers or 8 possible rational roots. Okay. So now what I want to do, this test says if there are any x-intercepts that are rational, this is going to be them. It's going to be one of these 8. Okay, so now what I want to do is pick one, and I want to synthetically divide. So I'm going to get the coefficients of my original polynomial, which is 1x cubed minus 3x squared minus 6x and a positive 8. And then I want to bring down my first one. Now this is where you might want to use Descartes' rule of signs. Descartes' rule of signs in my 2 cases. The only case that worries me is in the second case, my 2 positive x-intercepts could be 2 imaginary. So I might not have any positive x-intercepts at all. This is what case 2 tells me, right? But notice what always stays, because my negative didn't have 2 negative x-intercept possibilities and it stayed at 1, it never had 2 to give up, that I am guaranteed to have 1 negative x-intercept. Now that x-intercept might be irrational, so I might synthetically divide and all my negatives and not get an answer because this is only going to do rational numbers. But that's where I'm going to start off with. I'm going to pick my negative numbers because I know there's 1 negative x-intercept. guaranteed. In both cases, 1 and 2, Descartes' rule of signs said there's one negative x-intercept. So I'm going to start with -1 from my list here. And I'm going to say -1 times 1 is -1. I'd get -4. -4, I get -10. Get 10, remainder of 18. Now, our remainder theorem said this is the same thing as plugging in -1 into the function, and my remainder is my output. So I'm just going to collect these points on my graph as I go. Why not, right? I mean, it's not a zero remainder, but it is a point, -1 comma 18. Okay, the next thing I'm going to do is I'm going to pick another negative number. So I'm going to move to -2. And I'm going to bring down my same original. So I got to keep going until I find a zero remainder. -2 times 1 is -2. Add those together, get -5. I'm going to, you know what, I just realized that I did wrong up here. And y'all probably realized that. Let me backtrack. Mr. Pavlich did not add correctly. So I got a -4 here. This changed to a +4. And so this got me a -2. And then -1 times -2 is a what? +2. So I got a remainder of 10. So my bad on that. So the next thing I want to do is that would just change this number to -110. It didn't give me a zero remainder. Okay, so I'm back to -2. So I get -2 times 1 is -2. I get -5 when I sum those together. I get 10. I get +4 when I add those, and then I get -8. And I get 0 remainder. Now I know that, well, when I plugged in -2, my output was 0. So -2 is an x-intercept. So I'm ready to write that as a factor, x plus 2. Because it was a factor, that means these bottom coefficients are my coefficient to 1 degree less than my original polynomial that I was using to divide, which was my cubic. So these are the coefficients to the quadratic, which are x squared minus 5x plus 4. So notice I brought my cubic all the way down to a quadratic, and I found one of my factors. So now what would be nice if I could just factor this nice, easy quadratic. If not, I have to use the quadratic formula. So x minus 5 times x. Well, let's do not minus 5. Let's do x minus 4 times x minus 1. And these are all of my factors or zeros of my polynomial. So now I'm ready to write this in official factored form, which is x plus 2 times x minus 4 times x minus 1. What is my y-intercept? Well, let's go back up to the original polynomial. My constant term was 8. So I know I have a 0, 8 y-intercept. What about my x-intercepts? Do they bounce or cross? I have no bouncing because they all just occur once. And so which ones cross? -2, 0, 4, 0. What is my domain? You know that one is always going to be of infinity. What's my end behavior? Well, that's my leading term. My leading term was what? A positive x cubed. So this is an odd positive. So I know an odd positive is going to say the right end, positive infinity, always does what the sign says, so it's positive. So I know it opens up, and then they're at odds with each other. So the left end opens down. So I'm going to have this quadratic where the right end opens up, the left end opens down. And I'm going to put my x-intercepts on here. I have what, -2? Just a rough sketch. A 4, 1, 2, 3, 4, and a 1. And I know that and then I have my x-intercept of 8. 1, 2, 3, 4, 5, 6, 7, 8. And now I'm ready to work my polynomial. So I know I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And I know I'm going to come up, and I'm probably going to go up beyond my y-intercept. and I'm going to come back down and I'm going to cross through some minimum, and I'm going to come up and finish up. So notice I don't care about like what my min and maxes are, but I know this is going to be a min and this one would be a max. There's a lot of stuff on these equations, so my range would be negative infinity to infinity. But we'll practice a lot as we go through. All right, thanks.